Today's video will cover quantum tunneling. This is how particles pass through barriers that they shouldn't. Now, the core idea is that in classical physics, if an object doesn't have enough energy to get over a barrier, it will just stop. But in quantum mechanics, particles like electrons can sometimes pass through the barrier, even if they don't have enough energy to get over it. Now, this phenomenon is what we call quantum tunneling. It's real, experimentally proven, and it's actually used in modern technology. Now, here's a simple example. Imagine a ball rolling towards a hill. In the classical world, the ball doesn't have enough energy to climb the hill, it just rolls back. But if it does have enough energy, it will roll up and over, like seen in here. However, in the quantum world, the ball sometimes appears on the other side of the hill without ever climbing it. That's because this will pass through on the quantum level, where particles behave like waves, not solid points. Now, how it works is a quantum particle, like, say, an electron, is described by a wave function, which gives the probability of finding it somewhere. When this wave hits a barrier, part of it reflects, but another small part continues through. This means there's a non-zero chance the particle will be detected on the other side of the barrier. This is tunneling. The particle doesn't smash the barrier, it passes through probabilistically. Now, here's the mathematical insight, the light version. In quantum mechanics, the Schrödinger equation governs the wave function. When applied to the barrier, the equation predicts that the probability of tunneling is directly proportional to E minus 2kL. Now, K will equal how hard the barrier is, related to its height and the particle's energy, and L is the thickness of the barrier. The thicker or taller the barrier, the smaller the chance of tunneling. The thinner or lower the barrier, the higher the chance of tunneling. Now, here are the real-world examples of quantum tunneling. Now, nuclear fusion, which happens in the sun, is where protons in the sun tunnel through repulsive forces to fuse. This releases energy. Tunneling microscopes. Electrons tunnel between a metal tip and a surface, allowing us to map atoms, which is how we've got our structure from them. Semiconductors and quantum devices. There is tunneling used in these devices, transistors, and quantum computers. Radioactive decay uses tunneling. Alpha particles tunnel out of atom nuclei. Now, without tunneling, the sun just wouldn't shine, and much of modern electrics wouldn't work at all. Now, it's so weird, because in classical mechanics, particles can't break the rules of energy, but quantum tunneling happens because particles aren't just points, they're probability waves. Barriers aren't absolute, they are only reducing the probability. Now, nature allows the impossible events to happen, just with a very low probability. And this is possibly one of the clearest demonstrations that quantum reality doesn't follow your classical logical track of thought. Here are some of the interpretations. Again, you've heard this before. Copenhagen. The wave function extends through the barrier, measurement reveals the particles on the other side. The many worlds. In some branches of the universe, the particle reflects, in others, it passes through. And in the pilot wave, a guiding wave moves the barrier and the particle follows it along hidden paths. Now, here's a bit of a summary of what I've told you. So, the name of this is quantum tunneling. It was discovered in the early 20th century, explained by George Gamow in 1928. Here's what happens, is that a particle passes through a barrier. It classically shouldn't. What happens is because of wave-particle duality, and probability amplitudes. The real uses are in nuclear fusion, semiconductors, STM, and radioactive decay, and its significance is because how it shows the quantum world allowing improbable but real events. Now, here's your key takeaway. Quantum tunneling proves the universe isn't strictly deterministic. Even impossible events can happen, just with very low odds. But because reality at the smallest scales is governed by probabilities and waves, not hard boundaries. That is quantum tunneling for you. Thank you for listening. Stay smart.